Welcome to lecture number 15. This is the lecture of Wednesday, March 1st. And our topic is really changes of basis, describing vectors with respect to one basis or an alternative one. And we saw last time why this might be particularly a suitable thing to want to do if you want to describe a linear transformation, for example, that has some particular properties with respect to some vector, which might not be one of the standard basis vectors. For example, it could be a rotation about some axis that isn't one of the usual coordinate axes, and then maybe describing it with respect to a basis, which includes that a vector in the direction of that axis could be quite a useful thing. So really being able to move between different bases and being able to handle different bases is a fundamental business in linear algebra. So we're in chapter 3, and our theme really in this chapter, throughout the chapter, is going to be how certain bases can be suitable for describing linear transformations, and how the matrix that describes a linear transformation with respect to different bases how those matrices are related to each other algebraically as well as geometrically. But we're going to start with the question of, given a vector space and a basis for it, how does the representation of that, and given a vector in that vector space, how does its representation as coordinates with respect to one basis or with respect to another basis, how are they related to each other? So that's our basic question, and we'll give ourselves an example. So let's just say that we're working in R3, usual three-dimensional Euclidean space. We have the standard basis there, E1, E2, E3, consisting of the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, which is the basis with respect to which elements of R3 are generally typically written. Okay, and let's just suppose we also consider this alternative basis, B, which consists of these three vectors, B1, B2, B3, and we can confirm that those three vectors do form a basis of R3 by writing them as a columns of a 3x3 matrix and confirming that that matrix has an inverse, that its columns are linearly independent. Okay, and here's our question. Suppose we have any old vector at all in R3, for example, this vector 2, 1, 3. Okay. There it is written with respect to its standard coordinates. This is saying that V is 2 times the vector E1 plus 1 times E2 plus 3 times E3. And question is, if you wanted to write V as a linear combination of the three vectors of the basis B, there should be a unique way to do that because those three vectors are linearly independent and span R3. What would its coordinates be with respect to that basis? So another question is why we would want to be able to do that. And the answer to that is, well, regarding things like linear transformations with respect to which this vector might have some special property, like being an eigenvector, it would be convenient to be able to select bases according to particular scenarios that we're in that might not necessarily be the standard basis. Okay, so another question there, we will come back to it a little bit later in this chapter, but for the moment we'll deal with the question of, what are the coordinates of V with respect to the basis B? And I guess we can work these out, but we'd like to have a method that would allow us to take any vector at all instead of this V and not have to do a sort of complicated calculation for every one of them, but to have a method for doing this that would apply in general. So that's our plan. Okay, so question, what are the coordinates of V with respect to B means if we want to write V as a linear combination of the vectors B1, B2, B3, what should the coefficients be? Those are the coordinates of V with respect to B. Okay, so we know how V is written in terms of the standard basis vectors E1, E2, E3. Okay, it's 2E1 plus 1E2 plus 3E3. So if we knew how to write E1, E2, and E3 as linear combinations of B1, B2, B3, we could do the same for V because we know how to write V in terms of E1, E2, E3. So really we can answer this question for any vector V if we can answer it just for the standard basis vectors E1, E2, E3. Okay, so to figure out how to write E1 as a linear combination of the three columns B1, B2, B3, which are written here into this 3x3 matrix, what we need are the values of the coefficients x, y, z, for which x times column 1 here, which is B1, plus y times column 2 here, which is B2, plus z times column 3 here, which is B3, is equal to 1, 0, 0. And we can write this. This is a linear system of equations whose coefficient matrix has the columns of the basis B as its columns, as the entry elements of the basis B as its columns. So this is essentially the system of equations that we need to solve. And there are a couple of ways to think about it. One is to notice this matrix B again is a matrix whose columns are the elements of the basis B. We're saying that we're looking for the solutions x, y, z to the system of equations that says B, x, y, z equal to the standard basis vector E1. Okay, one way to deal with that, there are many. We can of course use our Gaussian elimination method for solving that system. We can observe that this equation can be rearranged to say the column vector x, y, z is equal to B inverse, the inverse of the matrix B multiplied by the standard basis vector 1, 0, 0. And that of course is just the first column of the inverse of B. Alternatively, looking at this version of the story that's written initially there, we can observe, okay, what we're saying is that the vector x, y, z, whose entries are the coordinates of the first standard basis vector 1, 0, 0, with respect to the basis consisting of the 3 columns of this 3 by 3 matrix B. Its entries have the property that when you put them in a column and multiply it by the matrix B on the left, you get 1, 0, 0. So basically that is saying that this column x, y, z should be the first column of the inverse of B, because that's exactly the property that it has. When you multiply it by on the left by B, you get the first column of the 3 by 3 identity matrix, which is the first standard basis vector. Okay, so yeah, so we're saying that the E1 coordinates, the B coordinates of the standard basis vector E1 are written into the first column of the inverse of the matrix B, which has the elements of the basis B as its columns. And similarly, by exactly the same kind of reasoning, with a 1 here in position 2 or 3 instead of position 1, we can observe that E2 and E3 respectively are columns 2 and 3 of the inverse of B. Okay, that's good, because that tells us how to write the standard basis vectors in terms of the elements of the basis B. And once we've done that, the thesis is that we can write any vector in R3 as long as it's written already in terms of its standard basis vectors. We can write it in terms of B. Okay, so for that example that we started with, then here's B. Here are the elements. The elements of the basis B are the columns of this matrix B. Okay, and here's the inverse of B. Okay, so we're saying that the first column of this inverse of B, that its entries should be the coordinates of the first standard basis vector E1 with respect to the basis consisting of the columns of this matrix B itself. And we can confirm that pretty easily by just noticing that if we take 1 times column 1 of B plus a half times column 2 of B plus a half times column 3 here of B, look at what we get in the first entry. We get 1 times 1 minus a half plus a half. That's 1. That's what we expect. If we take the linear combination of, if we take the element in the second position there, we've got 1 times 1 minus a half, so we get 0, which we expect. And in the third position, we've got 1 times minus 1, that's minus 1, plus a half times 2, that's minus 1 plus 1, which is 0 plus 0 times 1/2. So sure enough, we get 1, 0, 0 as the linear combination of the elements of the columns of B, whose coefficients are the entries in the first column of the inverse of B here. So of course we can confirm that directly for this particular example. Okay, once we know that, let's go back to the question of, given some vector V in R3 written in its standard form, how can we write its coordinates with respect to the basis B? Okay, so we know that this vector V, it's 2e1 plus 1e2 plus 3e3. So its coordinates with respect to the basis B, which we write like this, V with kind of square brackets around it and the name of the basis B as a subscript. Okay, this is 2e1, so its expression in terms of the basis B should be 2 times the expression for E1 with respect to the basis B, plus 1 times the expression for E2 with respect to the basis B, plus 3 times E3 with respect to the basis B. So each of these vectors with the subscript B, they're all column vectors, or at least they can be written as column vectors, and we know what they are. They're just the columns of the matrix B inverse. Okay, so what we're saying, again, interpreting this in terms of matrix vector multiplication, which is such a valuable mechanism for talking about linear combinations of vectors. This thing, by definition, this is just the linear combination of these 3 columns, E1, E2, E3, with respect to B, with coefficients 2, 1, 3. And that, by definition, is just the vector 2, 1, 3 that we started with, multiplied on the left by the matrix whose 3 columns are the expressions for E1, E2, E3 with respect to B, and those are the exactly the 3 columns of the inverse of B. So our conclusion is that the coordinates of 2, 1, 3 with respect to the basis B should be given by 2, 1, 3 multiplied on the left by the matrix B inverse, whose columns are the expressions for the standard basis vectors with respect to the basis B. And sure enough, we can calculate that product fairly easily. And what we get is 6, 9/2, 1/2 into 3 coordinate positions. And what that's telling us is that the vector V, whose coordinates with respect to the standard basis were 2, 1, 3, its coordinates with respect to the basis B are 6, 9/2, 1/2. And we can confirm that conclusion by direct calculation using the original expressions for B1, B2, B3 as given to us in terms of the standard basis. And I'll leave that for you to check. But basically, the columns B1, B2, B3 with respect to the standard basis were the three elements of the basis B, which were here on our second slide today. So we can confirm that conclusion by a direct calculation. And the point really here, I guess, is that there was nothing special, of course, about this vector V to begin with. This, if we replace 2, 1, 3 by any other vector whose coordinates with respect to the basis B we wanted to know, we'd have exactly the same process. Take that other vector and multiply it on the left by the matrix B inverse, which we can refer to as the change of basis matrix from the standard basis to the basis B. Okay, so it's just the inverse of the matrix whose columns are the elements of the basis B itself. So for any vector V, if you have it expressed in its standard form and you want to express it with respect to the basis B, all you need to do is multiply V on the left by that matrix, the change of basis matrix from the standard basis to B. This is the inverse of the matrix whose columns are the elements of B written with respect to their standard basis. So this concept of a change of basis matrix is something that's going to be important for us. And basically, it'll be a matrix which, by left multiplication, takes you from the coordinates of a vector with respect to one basis to the coordinates of a vector with respect to another basis. And our main use for that really would be to talk about the matrix of a linear transformation with respect to different bases, which will lead us in a couple of sections to the concept of similarity. So that was basically section 3.1 of the lecture notes. A few things that we've looked at recently to just recap on: how to recognize when a set of column vectors, a set of n column vectors in Rn or Fn for any field forms a basis, when you get an invertible matrix by writing them into the n columns of a matrix is the answer to that. I suppose the other thing is to recognize that elements of Rn or Fn in general, once we have a basis in mind for our vector space, immediately sort of become classifiable by coordinates, and that they have different coordinates with respect to different bases. And the third item is to use the change of basis matrix to write the coordinates of any vector in Rn or Fn with respect to a given basis when it's given to you with respect to the standard basis. Okay. Okay, so in section 3.2, we are back to talking about linear transformations. And what we're going to see is that every linear transformation can be represented by a matrix as soon as you have chosen bases for the vector spaces that are involved. So just to recap a little bit, supposing that V and W are vector spaces, not necessarily of the same dimension and not necessarily the same space, over some field F, which we can take to be the real numbers. And supposing that phi is a linear transformation from V to W. So just to recall what that means, it means that phi is a function that goes from V to W. And for any pair of elements in V, if we add the two elements together in V and apply phi to their sum, we get the same outcome as if we had applied phi to the two of them separately and then taken the sum of their images under phi over in W. That's the statement that the linear transformation respects addition, or that it's additive. And the other condition that we have to satisfy is that for any element V of the domain V, if we multiply V by a scalar from our field F, real numbers or whatever, apply phi to that scalar multiple of V, we get the same outcome as if we had applied phi to V first and then done the multiplication by lambda. And this must be satisfied for all vectors V and for all scalars lambda. Okay, that's what the linear transformation is. And of course, our vector spaces V and W might be something that kind of already lends themselves to a matrix description, such as spaces of column vectors, but there might be something more abstract, like spaces of polynomials or functions or whatever. Okay, so we know already that if we have a matrix m by n over the real numbers or some other field, then left multiplication by the matrix can multiply on the left column vectors that have n entries, and they give you back column vectors that have m entries that are linear combinations of the columns of A. So any matrix of size m by n by left multiplication defines a linear transformation from the space of column vectors with n entries to the space of column vectors with m entries. This example, for instance, defines a linear transformation from R3 to R2 to be the transformation that takes any vector ABC and sends it to the linear combination of the columns of the matrix whose coefficients are A, B, and C, which is that matrix vector product. Okay, so the images of the three standard basis vectors, of course, under that transformation are just the three columns of the matrix A. So that's like an example of a linear transformation that arises from matrix multiplication. the main point of this section really is that if you have any linear transformation at all, as soon as you have bases specified for V and W, then with respect to that choice of basis, every linear transformation actually has this form. It's just multiplication by a matrix. So that's what we're going to see in the next couple of slides. And to get there, we're going to use an example, which is not necessarily kind of already a matrix one, but an example that comes from a slightly different context. So next couple of slides involve an example. So supposing the vector spaces V and W have dimension n and m respectively, the assertion is when we choose bases for V and W, then with respect to these choices of bases, every linear transformation from V to W looks like the one in the last slide, a matrix product. So basically, the only kinds of linear transformations that really arise, at least once you've chosen to work with a particular basis, are these types that are encoded by matrices. And this is yet another reason why the machinery of matrix algebra is such a powerful tool for studying vector spaces, which do not necessarily arise only in the context already of matrices. Okay, so here's an example that's not such an ordinary one and that isn't already in an obvious way a linear transformation of Euclidean spaces. So supposing that we take the differential operator D, so that's just the operator that takes functions in whatever domain you're looking at to their derivative, just differentiates everything. Okay, and we're going to look at it on the space of polynomials because that's a nice vector space where we have finite dimensional subspaces that we can work with. So the differential operator D, operating on polynomials with real coefficients, is a linear transformation from the vector space of all polynomials with real coefficients to itself. And also, if we write as we've done before, P3 for the space of polynomials of degree at most 3 with real coefficients, and P2 for the space of polynomials that are at most quadratic, that have degree at most 2 with real coefficients, then the differential operator takes every element of P3 to an element of P2. If we apply the differential operator to a cubic polynomial, we get a quadratic as the outcome. And so there's nothing in P3 whose derivative is not in P2. Okay, so if we give ourselves a pair of bases for P3 and P2, we can choose any pair of bases, but I guess there is a sort of natural choice here. P3 is a space of all polynomials of the form ax cubed plus bx squared plus cx plus d, where a, b, c, and d are real numbers. So a sort of natural basis for P3 over the real numbers is the space of these so-called monomials x cubed, x squared, x, and the unit constant monomial 1. Okay, so the polynomial 2x cubed plus 3x squared minus x plus 1 is the linear combination of these elements with those particular coefficients. And equally, we can take x squared, x, and 1 to be the elements of a basis for P2. Okay, so for each of the elements of B3, we can look at its image under the differential operator D, which is a linear operator. It's additive and it respects multiplication by scalars. So for each of the basis elements of P3, which are written here, they form the set B3, that basis, we can look at its image under the differential operator and write that as a linear combination of the elements of B2, the basis B2. Okay, so D, so these arrows here just mean apply the differential operator D. Apply that to the first basis element from B3, you get 3x squared. X cubed derivative of that is 3x squared. Okay, that is the polynomial in P2, whose coefficients with respect to B2 are 3x squared plus 0x plus 0, 1. Okay, so it's represented with respect to B2, its coordinates are 3, 0, 0. We can write that as a column. X squared, the second basis element of B3, differentiate that, you get 2x. Okay, that is the element of P2, whose coordinates with respect to B2 are 0, 2, 1. 0x squared plus 2x plus 0 and 1. The third basis element here in B3, its image is 1. When we differentiate x, we get 1. That's the element of P2, whose coordinates in B2 are 0, 0, 1. And finally, 1, the fourth basis element in P3 is a constant 1. Its derivative is 0, which is the element of P2, whose coefficients with respect to B2 or any basis are just 0, 0, 0. So that is the 0 element of P2. Okay, so that is what the differential operator D does to each of the basis elements in our chosen basis of P3. Okay, so the B3 coordinates of any element, ax cubed plus bx squared plus cx plus d of P3 are given by the column a, b, c, d, of course, because the basis elements are just x cubed, x squared, x, and 1. And the B2 coordinates of the derivative of P are given by a multiplied by 3x squared. So that's a coefficient of 3a for x squared. We're differentiating p, we get from the bx squared term, we get 2bx squared. So we get 2 times b as the coefficient of x in the derivative. The cx term, its derivative is just c, and that's the coefficient of 1 in the derivative in P2, and the d part just gives us 0 when we differentiate it. So what we discover is that applying d, the differential operator, to a polynomial like this, and writing the result of that as a vector in P2, which means a polynomial that's at most quadratic, with respect to the basis P2 of P2, its coordinates as a column vector, are a times 3, 0, 0, okay, which are the coordinates with respect to P2 of the derivative of x cubed, which is the first basis element from P3, plus b times 0, 2, 0. These are these derivatives of the basis elements again, written with respect to the basis for P2, and so on. C times 0, 0, 1, d times 0, 0, 0. So this is nothing but the product of the 3 by 4 matrix, whose columns are the images under the differential operator of the basis elements from P3, written with respect to the basis elements from P2. So we have exactly the same thing happening. This differential operator, we're regarding it as being a linear transformation from P3 to P2, from polynomials at most cubic to polynomials at most quadratic. And what we realize when we write down the coordinates of any element of P3 with respect to our chosen basis for P3, those are A, B, C, D. Okay, so the polynomial here, written with respect to its coordinates, its coordinates with respect to B3 are A, B, C, D. So we can represent it as the column A, B, C, D with respect to B3. Okay. Its derivative is the column vector with 3 entries, which you get by taking this column and multiplying it on the left by this 3 by 4 matrix. The columns of this 3 by 4 matrix are nothing but the images under the differential operator d of the basis elements x cubed, x squared, x1, written as coordinates with respect to our chosen basis for P2, which is W. So this 3 by 4 matrix is the matrix of the differential operator with respect to the basis B3 for P3, the domain, and B2 for P2, the target of that operator, of that linear transformation. So its columns are the images of D, under the differential operator of the elements of B2, written as columns with respect to B3. And so again, this linear transformation, even though it goes between vector spaces that are abstractly defined, that aren't already written, in terms of Euclidean space, they don't operate naturally or immediately on elements of Euclidean spaces, we can actually still express it as a matrix product where the vectors and matrices are represented just as ordinary column vectors and ordinary matrices. Okay, so to apply this operator to any polynomial p of x, which I'm not really recommending as a way of differentiating polynomials, but you could do it, write the coefficients of p as a column vector and multiply it by this matrix, which is kind of almost diagonal, although it's not square. Okay, so of course the d never enters the product because all these zeros here meet the d in each column, and that fits because the derivative of the d gives us 0. If you have two polynomials that agree everywhere except in their constant term, they have the same derivative. So the result of this matrix multiplication process has the B2 coordinates of the derivative of P. Okay, if P is the polynomial whose derivative, which we start with, and whose coefficients we enter as the 4 entries of our column here. So the point of this example is not really in any way to recommend it as a method for calculating derivatives of polynomials, which I certainly don't. That's easy enough to do without resorting to these kind of matrix techniques. The point of it is to illustrate the fact that linear transformations, even which are defined in sort of abstract contexts, still amount to nothing but left multiplication by a matrix as soon as you have chosen a basis for each of the two spaces that the linear transformation moves between. It takes you from one space to another one. And by choosing bases for those two spaces, every linear transformation becomes just a multiplication on the left of column vectors by a matrix. So this is sometimes an extremely useful thing, either for kind of visualizing and conceptualizing linear transformations, or indeed for doing explicit, concrete calculations with them. So just while we're on this subject, let me mention that had we chosen different bases for our two spaces P3 and P2 to begin with, we would have ended up with a different matrix for the differential operator written with respect to those spaces. So just as an example to illustrate that point, and this is something worth thinking about, not necessarily again in the context of this example, where this is definitely not recommended as a method for calculating polynomial derivatives. The point is just to show that there is some arbitrariness in the choice of basis, and different choices of basis do give us different matrices. But every linear transformation can be written as a matrix with respect to some choice of basis, with respect to some, or indeed any choice of basis. Okay, so here's the same issue, the same problem, the same operator, the same linear transformation from the space P3 to P2. Okay, and so with respect to the basis B3 that we looked at earlier, which consisted just of x cubed, x squared, x and d, the coordinates of any polynomial are just its coefficients. Okay, and so we can write the derivative. But suppose we take a different basis for P3. Just keep the same one for P2 just to keep life relatively manageable for ourselves. But supposing that instead of the basis that we did take for P3, we take this other one. This is called C3. So the elements of C3 are x cubed plus x squared plus x plus 1 and 1. And the assertion is that C3 is again a basis for the four-dimensional space P3. Okay, to satisfy ourselves with that, we have to be satisfied that C3 is a spanning set for P3, or indeed that it's linearly independent, because those two things, as we know from the general theory, amount to the same thing for a set which has the right number of elements to be a basis of P3, which is 4. And certainly, if we think about a linear combination of these 4 elements with real coefficients, we can observe that they must be linearly independent. So if we want to write the zero polynomial as a linear combination of these 4, the coefficient of x cubed plus x squared must be 0, because that's the only one to involve x cubed. A non-zero coefficient there will lead to x cubed appearing in the result, because there's nothing else to cancel an appearance of x cubed coming from here. So if some linear combination of these 4 elements is the zero polynomial, the coefficient of the first basis element has to be 0, which means that we've got a linear combination of x squared plus x plus 1 and 1 equal to 0. The coefficient of x squared plus x there would have to be 0 as well, because if it isn't, then there's nothing to cancel the appearance of x squared that would occur from that. The elements x plus 1 and 1, again, same reason, they must be linearly independent, because any linear combination of those that would be equal to 0 would have to have 0 as its coefficient of x over all, and that means the coefficient of x plus 1 would have to be 0. So this is an alternative basis of P3 to the one that we used in the first version of this example. Okay, so supposing we want to write the matrix of the differential operator, the linear transformation that differentiates everything, with respect to this choice C3 of basis for P3, but with respect to the original choice B2 of a basis for P2, which is just x squared, x and 1. Okay, to do that, we have to look at the derivative of each of the elements of C3. These are our basis elements. Write them as coordinates with respect to the basis of P2. Enter those coordinates, respectively, into the 4 columns of a 3x4 matrix, and that matrix is the matrix of the differential operator with respect to these basis choices. Okay. X cubed plus x squared, when we differentiate that, we get 3x squared plus 2x. That's the vector whose coordinates with respect to B2 are 3x squared, plus 2x, plus 0 for 0 times the constant unit. Okay. So the C20 would be the entries of the first column. Second case, x squared plus x, the derivative of that is 2x plus 1. Its coordinates with respect to the basis x squared, x1 are just 0, 2, 1. So here they are in the second column of this matrix. Third element here, x plus 1, its derivative is 1, which is 0x squared plus 0x plus 1. So those entries go in the third column here. And the derivative of 1, the fourth basis element in C3, is 0. So its 3 coordinates are 0 with respect to the basis of B2. So what this is saying is that if we want to use this matrix to calculate the derivative of any polynomial in P3, so any polynomial that's at most cubic, for example, this fx, which is a cubic polynomial, what we need to do first is write fx as coordinates with respect to the basis C3. Okay, here it is written with respect to the kind of more obvious basis B3, which is the one we started with. But to write this as a combination of x cubed plus x squared plus x plus 1 and 1, we can observe it's got an x cubed in it with coefficient 1. So the coefficient of x cubed plus x squared would have to be 1. We've got 1 times x cubed plus x squared. That gives us 1x squared. We want 4x squared. So we have to add 3 more x squared. The only way to do that is to have 3 as the coefficient of x squared plus x in our linear combination. 3x squared plus x. Okay, that gives us so far x cubed plus 3x squared plus 1x squared. So that's x cubed plus 4x squared. That's right. We've got 3x. We want minus x, so we should subtract off 4 times x plus 1. And finally, that gives us the correct coefficients for x, x squared, and x cubed for f of x. But the constant coefficient so far here is minus 4. We want minus 2, so we should add 2 times the fourth basis element from C3. Okay, so this is saying that this particular f of x, its coordinates with respect to C3 are 1, 3, minus 4, and 2. To use a matrix product to calculate the derivative of this thing, we should take the vector 1, 3, minus 4, 2, multiplied on the left by the matrix of the differential operator with respect to the bases C3 and P2 of P3 and P2 respectively. When we do that, okay, we just do the multiplication. We get 3 times 1 plus 0 times the rest. So we get 3 in the first position. We get 2 times 1 plus 2 times 3 plus 0. That's 8 in the second coordinate position. And we get 1 times 3 plus 1 times minus 4. That's minus 1 in the third coordinate position. So we get the polynomial quadratic, whose coefficients with respect to x squared, x, and 1 are 3, 8, minus 1. So that's 3x squared plus 8x minus 1, which we can confirm is indeed the derivative of this f of x that we started with. Its derivative is 3x squared plus 8x minus 1. So the point of that sort of last part of the example was just to point out that we can write the matrix of a given linear transformation with respect to any choice of basis. If we change the basis for either the domain or the target space or both, the matrix will change as well. So this is the matrix of the same operator, the differential operator from P3 to P2, with respect to the basis C3 of P3 and B2 of P2. It's not the same matrix as we had on the last slide, which was the matrix of the same operator, but with respect to a different choice of basis. So one of the things that we're going to do as we proceed through this chapter is just kind of figure out how to organize this a bit better. I mean, this example, I don't expect you to sort of spend time on it or to sort of produce alternative versions of it, and certainly not to use it to calculate derivatives. That's not the point at all. The point is to show that how by choosing a basis, we can obtain a matrix description of any linear transformation, even between spaces that aren't sort of naturally or originally expressed in terms of matrices. But the choice of basis is crucial, and the matrix that you end up with does depend on the choice of basis. Sometimes there's a very obvious choice of basis, and for the first version of this example, there was an obvious choice of basis for the two spaces of polynomials, P3 and P2, and here they are. But it may happen in other cases that there isn't really a particularly natural choice of basis, and you just have to pick one. Or there may be a choice of basis that's suitable somehow for what you want to do with your example, but it might not be the most obvious choice of basis if you didn't have a context in particular that you wanted to look at. So I suppose with this example, what I kind of recommend doing with it is just kind of checking the details, thinking about it in terms of how to take a linear transformation that isn't necessarily already kind of expressed in terms of matrices, and recognize that by choosing bases for the two spaces involved, we can realize it as left multiplication by a matrix, representing the differential operator with respect by using matrices. Is not particularly something that I'm saying is arises very frequently or is necessarily something that you want to do, but it's an example that illustrates the point. Okay, so that's the kind of idea of representing any linear transformation as a matrix. Okay, so just to finish up today then, we will have a look at the topic that we're going to discuss in a little bit more detail in Friday's lecture, and that's the kernel and image of a linear transformation and the rank nullity theorem. These are concepts that are reflected sort of throughout abstract algebra generally, but they occur in particular in the context of linear transformations. So let's put ourselves back in the context of a general linear transformation between finite dimensional vector spaces, which we now know can be expressed as a matrix product as long as V and W are finite dimensional and we have bases in mind for them. But in general, without having to choose a particular basis, we have the concept of the kernel of the linear transformation phi. So the kernel of phi, which is denoted by KER for kernel, is a set of elements of V whose image under phi is the zero vector of W. Okay, so it's a set of vectors that when you apply phi to them, you get the zero vector in W. Okay? The kernel is always a non-empty subset of V because it always includes at least the 0 vector of V, but it can be bigger than that. The image of phi is the image of phi as a, just as a function. It's the subset of W consisting of the images under phi of all the elements of V. So it's the set of elements of W that arise as images of elements of V. And the claim is that the kernel and image of phi are subspaces, respectively, of the vector spaces V and W. So just to recall what that means, it means that if you have a pair of elements of the kernel of phi, then their sum also is in the kernel of phi. That's something that's easily verified from the definition of being in the kernel. If you have two elements whose images under phi are both 0 in W, then when you apply phi to their sum, you get 0 plus 0, which is again 0. So their sum also is in the kernel. And multiply an element of V by a scalar doesn't change the fact that its image under phi is 0. To kind of verifying these things is straightforward, but it uses the full definition of what it means for phi to be a linear transformation, that it respects the addition in V and that it respects multiplication by scalars. And for similar reasons, the image of phi also is a subspace of W. And that kind of raises a question, because if V and W are finite dimensional, then the kernel of V is a subspace of V, the kernel of phi rather is a subspace of V whose dimension is some positive integer at most equal to the dimension of V itself, and the image of V is a subspace of W whose dimension is at most equal to the dimension of W as a vector space. So these concepts of kernel and image kind of allow us to attach two more non-negative integers to this linear transformation, namely the dimension of the kernel, which is at most equal to the dimension of V, and the dimension of the image, which is at most equal to the dimension of W. And we're going to be able to say a little bit more about the connection between those two numbers, which is the rank nullity theorem. Just as an example, if your matrix is, or if your linear transformation is already expressed as left multiplication by some matrix, then you can give a particular interpretation to the concept of the null space and image in terms of matrix algebra. So just an example, and then we'll defer the discussion of the rank nullity theorem until next time, is suppose we have the linear transformation from R3 to R2, which takes elements of R3, those are column vectors with 3 entries, multiplies them on the left by this matrix A to get a column with 2 entries. Then the kernel of that linear transformation consists of all vectors in R3, which is the domain, with the property that when you multiply them on the left by this matrix A, you get the 0 vector in R2, which is the vector whose coordinates are both zeros. Okay, so that's the set of all vectors x, y, z, which when you hit them on the left with this 3 by 3 matrix, you get the 0 vector. Okay, so in the matrix context, this space is referred to as the right null space of A. Right because they're columns that appear on the right in the product, they're multiplied on the left by A. There's also a left null space of A consisting of row vectors with 2 entries, with the property that when you multiply them on the right by A, you get the 0 row vector. But let's stick to the setup. The right null space of A is a set of all column vectors of length 3, which when you multiply them on the left by the matrix A, give you the 0 vector. Okay, and we can find it, of course, by interpreting this problem as a system of linear equations and applying row reduction to the augmented matrix, which would have this matrix A in its first 3 columns, and if you want to write them, the 0 column in the right-hand column in the augmented matrix, you can leave out the 0 column and just have it there kind of implicitly in the background if you want. What we find in this example is that the vector minus 5, 1, 7 is in that right null space, and so are all of its scalar multiples. Okay, so we find that when we apply the Gaussian elimination, as we'd expect, we have a system of equations with 3 variables, x, y, z, and only 2 equations. So we would expect, as long as the system is consistent, that one of those variables would be free. And sure enough, if z is a free variable, what we find in the solution is that the value of x should be minus 5 over 7 times the value of z, and the value of y should be 1 over 7 times the value of z. So the solutions are all scalar multiples of that vector minus 5, 1, 7, which form a one-dimensional subspace of R3. It's a subspace of dimension 1. Okay, that's the null space. And then the image of the left multiplication by A linear transformation is the space of all vectors that you can get by taking this matrix A and multiplying them by something, by some column vector x, y, z. That just gives you all linear combinations of the columns of A with coefficients x, y, z. So no matter what x, y, z are, we get all such vectors. So what we get exactly is the linear span of the 3 columns of A in the vector space R2. Okay, so in the matrix context, this is called the column space of A, as we saw last time when we talked about row rank and column rank. So in this example, the space is all of R2, since the first two columns of A, for example, form a spanning set for R2. So what we have in this example is we have a vector, we have a linear transformation from R3 to R2, defined as left multiplication by this matrix A. What we discover is that the kernel of that linear transformation is the right null space of A, which is a one-dimensional subspace of R3. It's a set of all scalar multiples of -5, 1, 7. And we see that the image of this linear transformation is all of R2. It's the column space of A, which consists of all vectors in R2, because the first two columns of A, for example, in fact, any pair of columns of A, are linearly independent and form a spanning set for R2. So what we see in this particular example is that the dimension of the null space, which is 1, if we add it together with the dimension of the image, which is 2, we in fact get 3, which is the dimension of the domain, or 3 of the linear combination. So, this linear transformation applies itself to R3. Everything in R3, which is a three-dimensional space, is in the domain of this linear transformation. What we discover is that the kernel is one-dimensional and the image is two-dimensional. And even though the kernel and image are not subspaces of the same space, the kernel lives in R3, the image lives in R2. Nevertheless, when we add together their dimensions, which are just the positive integers, 1 and 2 in this case, we get 3, which is the dimension of the domain. And the comment for now, and we'll revisit this on Friday, is that this is not a coincidence. It's a special case of it's an exemplar or an illustration of the rank nullity theorem, which says that property holds in general for any linear transformation. The dimension of its kernel plus the dimension of its image will always be equal to the dimension of the domain. So we'll come back to this point on Friday, and we'll pick up with the discussion of the rank nullity theorem, and then we will move on from there to the question of how we can describe a linear transformation from a finite dimensional vector space to itself with respect to different bases and why we would wish to do so. That's it for today. Thank you very much, everybody, and see you on Friday.